Okay, thank you very much. First of all, I would like to thank you for this nice invitation, also to Georgia for this invitation. I'm very happy to be here after a few years because actually I was giving a similar course here in this place, the same room. I think it was 5 years ago, the last one. And since I know that not everybody in the audience should be interested in fluid mechanics, in particular in the equations I'm interested in, so it was a very difficult choice for me what kind of talk I should give. Because there are basically two extremes. Either you just talk about what you like and you use all the technicalities, then you risk that maybe 80% of people is not going to understand you, or you make it very popular, then it will be too boring. So, well, I decided to tell you something about what is new in my field, which actually there are some groundbreaking news in the field of fluid mechanics recently due to some people I'll mention in my talk. And so I would like to tell you something about these changes now. And of course I'll have to use some terminology. In particular, I have to write down some equations on the blackboard, so I hope you don't mind. Please don't hesitate to tell me if something is completely not understandable or whatever. I know it's always difficult to say that because it starts from the very beginning. But anyway, so I'll speak about some equations in fluid mechanics. And okay, there are several systems. So to make things, I would say, easier, I would start with something what is called, it's already not very easy, with something what is called compressible Euler equations. I'll first write down the equation, then I explain the meaning, right? So this is, okay, some people don't like, actually I should say compressible Euler. Actually, some people don't like if I say that. I'm very sorry about this wire, but I'm not really used to this technology. Anyway, some people don't like if you say even compressible, because they say in this context you say compressible equations, but it's not the equation that is compressible. They are equations of compressible fluid. So these are equations that describe the motion of a compressible of a general fluid, for instance, the air in this room. Of course, you may believe or not if these equations are exact. Actually, we will see that now there is a good reason to believe that they are maybe not completely optimal for describing what is going on in fluid mechanics. So these equations use only two variables. So I am ignoring a lot of things, of course. I am ignoring the whole complexity of the problem. I will describe everything in terms of two variables only. The first one, which is usually denoted by rho, is called density of the fluid. So density is a quantity which tells us how much of mass I have in a given volume element. So the density itself is a function of t. T is always time. And in my talk it will be also a function of x. And the interpretation of this function, I told you that either it's very elementary or completely new for somebody. So I have to make a compromise. So I apologize to those for whom it's already very well known. So the meaning of the density is that if you take this function, so this is a function of time and of t and x, you take a volume element b in your fluid in the space, like say the reference domain for me is this room here. I integrate this at a given time over x, and the meaning of this is the amount of the mass is the total mass of the fluid which is contained in this volume element. And of course, this mass changes in time if I admit that the fluid is in motion. Actually, I'm always interested in fluids that are in motion. I'm interested in fluid dynamics, which means that the fluid should move. And so it's also a function of time. And by interpretation, by physical meaning, of course, the density should be a non-negative function. Actually, you may object even this non-negative. Okay, everybody knows that this should not be negative. The density should not be negative because otherwise we would get, in certain cases, the mass of some certain volume would be negative, which doesn't make any sense. However, you can allow the density to be zero because this corresponds to the so-called vacuum. Vacuum is the hypothetical state of matter. Of course, everything holds to a certain extent. I am still assuming that I'm at the level of classical physics or continuum mechanics, so I still assume that the air or the fluid is a kind of continuum. Everybody knows that it's not really the case, that the fluid is composed of many particles and so on. But I stay at that level, so I assume that the fluid is continuum. So to have density to be zero, it's not really against the nature, because this means that there is simply no fluid in the given volume element, so there is a vacuum. However, all the models I'll talk about were derived under the assumption that there is no vacuum in the fluid. So actually the state when rho is 0 is not really desirable. So we should somehow be able to exclude it. But as you know, in mathematics, one thing is that what you suppose in physics, and one thing is what is allowed to you by the equations. So it might happen that in your equations, even if you start with a nice distribution of the density, the equations are so bad that they will describe the situation in such a way that the density may become 0, which of course may be interpreted in several ways. One of them is that your model is not good. The other one is that maybe the model is good, but there is vacuum under certain circumstances, and so on. So that's one of the issues actually we should discuss in this lecture. But of course, I don't know if we go that far in order to have some discussion on that. Okay, so that's the density, and the second variable I will use. So the density is changing in time because the fluid is moving. So there should be some way how to describe the motion of the fluid. And so again, I'll stay at the level of classical or continuum mechanics, and I'll assume that the motion of the fluid is described by a vector field. Sometimes I will omit to write this arrow here, but it's a vector field, which again is a function of t and x, and this vector field is called velocity. And so I assume that at each point x and at each time t, I am given a vector field like this one, which describes the motion of the fluid. So in particular, if you like to see how the fluid is moving, you just solve this ordinary differential equation. So x is a vector valued function, so you take its derivative with respect to time, and you solve it. So you assume that you are given this vector field, you solve this ordinary differential equations with some initial conditions, which is the initial position of your fluid particles, and these solutions of this equation should give you the position of each hypothetical particle of the fluid after a certain time. So that's the meaning of velocity. And now for these two, and I'll assume that the fluid is described fully by these two quantities. So I'm neglecting a lot. For instance, we know in practice that of course what is essential for the fluids in motion is also the changing of temperature. So for instance, if the fluid is hotter here and colder here, then this will create some kind of motion. I'm completely neglecting in my talk any effects of the temperature changes. So I'll just concentrate on these two variables, which sometimes, such a model is sometimes called barotropic. If you don't like the name, you just forget it. And so I am ignoring the temperature. There is no temperature effect. And in my talk, I'll also ignore something what is called viscosity, which makes the problem less interesting because now the famous millennium problem is not included. What means viscosity? Viscosity means that each fluid, even though in some cases it could be neglected, each fluid is viscous in the sense that, the motion is never perfect. In the sense that there you can always observe some kind of friction between the two parts or two volumes, volumic parts of the fluid. And this friction, of course, produces heat, and so the heat changes the temperature. And because I don't want to see the temperature in my model, I also don't want to see viscosity. This is not really connected. I mean, you can neglect temperature but still keep viscosity. But I also neglect viscosity, which maybe is the source of my problems later on. So I assume that the fluid is so-called perfect, so there is no viscosity in the fluid. And under these circumstances, you can write down the basic physical laws. The basic physical laws are actually, so partial differential equations which are used in continuum mechanics are always derived from some physical laws. These laws are called conservation laws or balance laws, depending on the character of your problem. So I will assume a very idealistic situation that there is absolutely no force acting on the fluid, not even the gravitational force. Actually, if there was a gravitational force, I could include it in the equations without any extra difficulty, but I'll assume that there is no force acting on the fluid, so the equations will express only two physical laws. One law will be conservation of mass, and the second law I'll use is conservation of momentum. And these two equations should be enough in order to describe the motion of these two quantities. So, and what we obtain is the so-called Euler system. So conservation of mass is an equation which, so in the course I gave here 5 years ago, there was one lecture devoted how you can derive this. So you actually start with the principle that you have a mass element, volume element here, and then you consider the whole amount of fluid in this volume element. You let the fluid evolve in time. You compare the amount of fluid at the time t1, at the time t2, and you admit as a kind of scientist that actually there is no other possibility to remove or create the mass inside of this volume unless something escapes or comes in through the boundary. And if you write down this, and if you do the so-called, what was done basically for the first time by Newton, so you assume that this volume you are considering is infinitely many small, was probably not very correct English, and if the time is infinitely short, then you end up with a kind of differential equations for the density and for the velocity. And these differential equations is actually mathematical expression of conservation of mass. You are already assuming something which may not be correct in the future. You are assuming that all quantities you work with are continuous. So it means, of course, we are mathematicians, so we know that not every function is continuous. So there might be functions which change value in time, and this change may be abrupt in the sense that at a certain moment there might be jump up, jump down, and so on. Well, in this derivation, you assume that everything is continuous. That's why everything is also called continuum mechanics. And the first equation you obtain is the conservation of mass, which is in this form. So this is a partial derivative of the function rho with respect to time, because we know that it's a function of two derivatives. Plus, well, this is divergence of this. So, okay, if you don't like this notation, this is the same as if I take the sum. I goes from, okay, I'll be always in the three-dimensional physical space, because this is somehow, okay, if I don't say otherwise, it's somehow the physically relevant. So if you don't like this notation divergence, so this is nothing other than the partial derivative, because x, the variable x, has three components. It's a vector. So this is the sum of dxi rho ui. This is exactly what is written down here. And so the whole thing is an equation which expresses the conservation of mass. And there is only one, and I have two variables here. I have rho and I have u, so apparently I need another equation. And this another equation, it's another physical principle which is used in this, and this is called conservation of momentum. And conservation of momentum is basically mathematical formulation of the Newton's second law. And so if I write down conservation of momentum using basically the same arguments, I did not explain anyway, conservation of momentum, I end up with a second equation. And it's very simple, because in my case, there is no viscosity, so the conservation of momentum is like the time change of momentum, which happens to be this function here. Again, I use this symbol divergent, then I explain what I mean if you don't like it. Divergence, I use, actually I write it in this way. I'll explain in a minute what it is. And there is a gradient of the pressure of a function which depends on rho, and this function is called pressure. So actually this function P is a given function, and typically the pressure P of rho is takes the form A, which is a positive constant, times rho to the power gamma, where gamma again is something which is greater than 1. And there is some physical meaning. So again, there is some notation here. So this is a vector equation, right? It has three components. So if I write down this component-wise, in order to know what we deal with, what we are dealing with, I can write this. So this is actually the sum j goes from 1 to 3 dxj rho ui uj. That's the meaning of this notation. And so I have, so to make the long story short, I have two equations. I have 1 and 2. And they are supposed to describe the motion of the fluid. So now to make things simpler, yes.
So if you imagine it as a gas,
yes,
a bunch of small particles. What does the second one express? What is the
conservation of momentum, which means that acting on a volume, you take a small volume of your gas, you act by a force on this gas, and you compute it in which way the momentum of this small volume reacts to the force. But because there is no external force, the only force in the gas is a force which, and there is no viscosity, so there is no friction between two parts of the gas. So the only force comes from this, from the fact that actually the gas is compressible. And so if you compress it, if you squeeze it, then you can feel some resistance in the gas, which is exactly this force here. This is the gradient. I did not explain the meaning. Okay, there's a lot of notation here. So this is actually a vector which is defined like dxi of 0. So this is a mathematical, of course, there would be a long story to give an exact derivation of that, but I'm sorry that there's no time for it. So we have these two equations, and you may believe in them or not, but they are supposed to describe. So if you are familiar with maybe more popular incompressible model, which consists also in adding viscosity here, you would get the so-called Navier-Stokes system. But here we don't have Navier-Stokes. This is called Euler system because there is no viscosity. In the Navier-Stokes system, we would have something like Laplacian of u on the right-hand side, which represent the action of viscosity. And so for those who work in the theory of partial differential equations, of course, you know that there is a big difference between the equation when there is Laplacian and where there is no Laplacian. Because with Laplacian is a kind of parabolic equation, although not exactly, because we still have the first equation that is not parabolic. Without Laplacian is something what is called hyperbolic. So let me explain shortly what is the main problem here. Okay, so before finishing formulation of the problem, so now you should, okay, so there are two things you should prescribe now. So we have a system of equations. So I prescribe, so I would like to, the model should describe the evolution of my system. So if you give me the state of the system at a certain time, which is usually fixed to be 0, because basically this system is autonomous. There is nothing which would depend explicitly on time. So you can start with the time 0. This is the usual convention. And so what you prescribe are the so-called initial state or initial data. So initial state of the system is prescribed by the density. So somebody tells me what is the density distribution at the time 0. So this is a given function. And I will assume that it is positive everywhere. I don't want to consider vacuum. And the second thing is that somebody should tell me what is the value of the velocity at the time 0. So this is also a given function. And okay, so now in each case, you know, the gas is never like filling up the whole universe. There is always some kind of what is called boundary conditions. For instance, I can think about the gas which is in this room, but there are some walls and they are impermeable, so the gas should not escape through the walls and so on. But in my talk, I'll assume something very, very simple, which is, however, very often used, which is the so-called periodic boundary conditions with respect to x. So I'll assume in my case that all functions are periodic in x. This has nothing to do really with any physical observation, which means that I assume that rho t x plus a certain number is the same as rho t x for any x, and the same with u. And of course I assume the same for the initial data. And so there is nothing, this has nothing to do with periodicity of the motion. This has nothing to do, because this is periodicity with respect to space, not in time. So you may think about the motion which is periodic in time in the sense that the state repeats after a certain period. Here no, here what we have is periodicity in space, which means that actually this is a mathematical way how to get rid of the boundary conditions, because the boundary conditions usually represent some kind of extra difficulty. And of course, if you really want to have a physical model, you should replace this by something else. But for simplicity, for the presentation, I'll assume this, which is very often done in the literature, which means that basically you take your domain and you are in a position that you say, okay, so I'm not really interested what is going on very far away. I'm interested in the density in some volumes of space, and I'm interested in the velocity in some volume of space, and everything what is far away is just irrelevant. And so I can take this period very large and I extend everything periodically. So many people who are not really familiar with usual techniques in fluid mechanics immediately object that this is not correct. But in a way it is correct if you admit that this system has a kind of property which is called finite time of propagation. which means that actually what is going on very far away does not influence the system in a finite time, provided you take the period very long. So you may say, now I am cheating, but of course I'll be cheating many times, but this is the usual cheating, at least in the literature I know. And this is my problem. So mathematically now, let's go to mathematics, let's forget about physical background. And let's switch to mathematics, and so this is our problem. So our problem is, you give me the initial distribution of the density, you give me the initial distribution of the velocity, they will be periodic with respect to the space variable, and I would like to have a solution, so I would like to have a couple of functions which do satisfy the system of equations. So the system of equations these are partial differential equations, because there are partial derivatives. My functions depend on many variables, in particular 4 variables, 1 time variable, and 3 space variables. Actually, these equations make sense also in 1 space variable. You can think about the situation when the gas is actually confined to something like a very thin tube, and so everything depends basically only on 1 variable. Or you may think about the case when they are functions of 2 variables, in the case when the gas fills up some kind of plane and you don't care about the thickness of the plane. And so, so you may think that this problem is this problem makes sense. So if I denote by n the dimension of my physical space, actually it makes sense to consider everything in 1, 2, 3 space dimensions. So the first observation that it is a system of partial differential equations. The second observation is that a system is nonlinear. It is nonlinear for many things. For instance, this term is nonlinear. It's a product of 2 functions. This term is nonlinear because it's a product of 3 functions. This term is nonlinear because the pressure in general is a nonlinear function. And so my task is now to say, okay, give me the initial data, and I would like to know if the system has a unique solution for this initial data, if possibly defined for any time interval. And so for those who are familiar with the theory of partial differential equations, you know that this might be a difficult problem, because this is a nonlinear equation. And so we know from the theory of ODEs, for instance, even if you solve a very simple equation like the equation, okay, let's write it as ODE. So maybe even if you want to solve something like that, which is an equation, the time derivative of some function y is equal to y squared. So this is a nonlinear equation. We know that for this problem, it's a very simple example of a problem where solutions may not exist for any time. Actually, if you solve this equation explicitly, you may find out that solutions of this equation, depending on the initial state of this y, will behave like that. So after a finite time, they will blow. This is usually called blow up. So the solution doesn't make sense after a finite time. And because you see that here we have also quadratic nonlinearity in U, so there is a risk that the same could happen for this system. And so in general, this is so solving this problem, even showing that there is a solution. So I would like to address very simple question. I mean, is there a chance to get a solution of this problem? Is the solution defined for any time, any positive time? Because here, for instance, on this example, we see that the solution is defined for a certain time, but after this time, it becomes sort of infinite, or there is something wrong in the solution. And the second and the last question is the problem so-called well-posed? Means, is there a chance to get a unique solution of the problem? Okay, so let me say a few words about this. So first of all, okay, so now I am really using some elements or some facts from the theory of partial differential equations, so I apologize to those who never studied this topic. Okay, the first question, because it's a nonlinear system, so the first question people ask is, assume that we have a nice initial data, which means nice means that, okay, the initial data, rho 0 and u0 should be nice functions. You don't want to have problems from the very beginning, right? So you want to impose something like that, for instance, rho 0 is a C infinity function or something like that, very smoothly differentiable, the same with u0. And of course, you don't want to have any vacuum. This is what I already said, so you can assume also this. And so the question is, can we have solution of this problem, and is the solution uniquely determined by the data? It should be the case, because it's a model of fluid. Everybody knows that basically, or everybody believes, of course this is a matter of philosophy rather than mathematics, that if you give me the initial state, if the model is correct, then there should be a unique solution. I mean, we are deterministic. Everything I'm talking about classical physics. There is no quantum mechanics, nothing like that. So the model should be deterministic. So given the initial state, there should be unique solution. Well, the answer is yes, but to a certain extent. If you give me nice initial data, I really don't want to specify how nice they are. For people who are familiar with the theory of Sobolev spaces, I can go to some Sobolev exponents here, which are like dimension plus 2 or something like that. I don't care about it. So let's assume that I have nice initial data. Then it can be shown that for a certain time, there exists a time which depends in general on these data. So let's denote it by t0, which is positive. In some cases, you can even determine what is the lower bound, but we don't know what is the upper bound. And for this time, the solution exists. The solution is classical, which means all derivatives which are written down here exist in the classical sense. The solution is differentiable. So there exists what is called classical solution. Of the problem, and it is unique. But now, each time in mathematics, when you speak about uniqueness, you should, this is always, not always, but very often this part of problem is omitted. If you say unique, you should say in which class it is unique. Maybe unique in the class of measurable functions, which means that if you have any other measurable solution, they must be the same. Okay, so here I claim it is unique in the class of smooth functions. So, which means that if you give me the same initial data, I cannot find two different classical solutions on this time interval. So the solution is unique in the class of strong solutions, but there is a point in this interval is not necessarily what you want. It may be very short. This t0 on which you know that the solution exists and it is unique may be very short. At least mathematics gives you, the answer of mathematics is there exists such a t0. And so, of course, the optimal result you would like to have, because it's a model you would like to use for predicting, say, meteorological phenomena, you would like to know that this t0 is actually infinity or at least as large as you want. And well, so the problem is this true? I mean, so the first question which arises here, of course, all these problems are nowadays classical. Yes, but this is periodic in x, not in time. We are talking about, there are two things. Just forget this. It's just misleading. No, there is nothing like periodicity in time. No. And so this is a local solution in time. Everybody know, again, I'm saying trivial things for people working in differential equations. And it could be, but maybe not, that the solution will do this. No? So there will be some critical time, and maybe the norm of this solution will become infinite, whatever. And so that's, of course, nowadays all these are questions which are well known. I mean, the answer to these questions, at least in the case of this particular system, are well known. So, by the way, how much time do I have? I said 1 hour.
Until 4.
Sorry?
Until 4. So
Until 4. Okay, so that's fine. So I still have half an hour. Okay, so the first question, unfortunately, the answer is no. So it's not like only a problem of mathematicians who are not so clever in order to find out that actually the solution exists globally. You can show that there exists initial data which are nice. They are smooth, very decent. After a finite time, the solution breaks down. But it does not break down in the sense you would expect at the beginning, like something like that the norm of the density, that the density becomes infinite at some point. No, the solution breaks down in the form of a singularity which is called shock wave. And this is rigorously proved. So that's nothing theoretical. I mean, that's nothing you may expect or not. That's something what really happens. There are examples. And so the solution may develop shock wave. And so the shock, so let me take, for instance, the density, and let me try to suggest what may happen. So the density could be, so let's take the density at the time t. So the density could be a function which looks like that. And now when times go on, it happens that because of nonlinearity, some parts of the fluid which are here, of course this is a very naive picture. I'm not really plotting any kind of exact solution of the problem. But basically the reason is that some parts of the fluid move faster than the other ones. And this depends on the density. So when time goes on, you may have something which is steeper and steeper. And at the end of the day, you end up, and at a certain moment this breaks down, and so the density becomes discontinuous. Of course, at this point, you have no derivatives, so it looks like everything is lost. Okay, so now you have two possibilities. Either you believe in these shocks, that's something what really happens. For instance, if you observe some supersonic plane, you may see something like when the plane breaks this sonic barrier, then you can see some kind of really big bang, which sort of corresponds to this shock. So there are two philosophies. Either you say, okay, the system is not good, it describes only phenomena for a short time, but for a long time it's not convenient, I have to invent something else. Or it describes everything up to the shock, or you believe that the shock is something what is there, what should be included, because each model is a kind of approximation. So of course you may say, I don't like discontinuous solutions because they don't correspond to the continuous picture. Maybe the shock is really smooth, and maybe it's because we neglected viscosity, which is what many people believe. But anyway, the problem is simpler without viscosity. So you may adopt another point of view, and you may say maybe the model is not so bad. After all, it's a kind of approximation. But maybe I can have a different concept of solution for which the shocks are somehow allowed, because we know that they are unavoidable. But still, maybe I have a unique solution, and maybe I can compute it numerically. Okay, so this new concept is the so-called weak solutions. Yes.
Just a question. So if you assume, I mean, this compressibility, this seems to be also a problem with compressibility. If you assume that you cannot compress,
if it's incompressible,
then this is the only barrier. Otherwise, there is
the incompressibility is a delicate issue. Yes. So if you assume that the fluid is incompressible, then you get some analog of these equations when the density is constant.
No, I don't mean that it's incompressible. I mean that if there is a barrier against compressing it. If you compress it too much, it pushes away.
Oh, if you do some barrier, you have to include it in the equations, right? Then you get a different system.
But then you would, if you include that, would you have a solution always, or you would?
It depends what you include. Huh? Yeah. I mean, you may include whatever. You may assume, for instance, that the pressure becomes very large. You may include viscosity, for instance, as a barrier against compressibility. Because if there is viscosity, of course, the viscosity will cause the shock to smooth. Huh? But it is an open problem whether or not for problems with viscosity you have shocks or not. This hasn't been proved. I mean, everybody believes there is no pure shock in the sense of like they would survive forever, but there could be some singularities. We don't know. Huh? But here we know. Here, the answer is positive. There are shocks. There is no way to work with classical solution of the problem. So what people did was they invented, or they introduced something what is called weak solution. Well, shocks are sort of turbulence, right? But depends what you call turbulence. I mean, that's a very delicate issue. Some people call turbulence just chaos in the sense of a dynamical system theory, and this may occur also if there are no shocks. Huh? I mean, the turbulence could be that you just define turbulence like instability of the sense that if you have two initial data closing out, then after a certain time they will be very far away. Right, so you get some kind of exponential instability with respect to the initial conditions. Of course, shocks are related to turbulence, but these are two different things. Huh? I mean, I'm just talking about these equations, and we are at the level of mathematics. I'm not including anything else. Okay, so what people invented are what is called weak solution. Weak solutions, again, so because I don't have so much time, so let's do it quickly. Weak solutions basically admit discontinuities. Huh? So how they are defined? There is a long story again. There is a certain physical background that you may use in order to derive the weak formulation. But very roughly, what you do is that, okay, so let's take this equation here and let's multiply it by some function phi, which is a smooth function. Phi is smooth, and I assume that phi is also periodic in x, and phi has compact support in time. And if I do it, and then I integrate with respect to space-time. I do integration by parts. This function has a compact support. So I can do integration by parts, and I can put all derivatives on this so-called test function, and I don't get any boundary terms because the phi is compactly supported. So if I write it very quickly like that, what I end up with is this integral formula for any phi which is, say, C infinity, but you don't need it really, and compactly supported. And you do the same with the second equation. Of course, in the case of the second equation, the function must be vectorial. So let's call it psi. Okay, I'm sorry again for this notation. This means, this double dot means that you take the sum over all indices. It's not really important here. The important thing is the interpretation of this. This is psi, this is equal to 0. Again, for any psi in C infinity, the support of psi is compact. So this is called weak formulation of the problem, right? So instead of working with derivatives, you work like with functionals. You look at the equation like being a kind of functional applied to the set of smooth functions. So the advantage of this definition, and you say that you have a weak solution of the problem if these two identities are satisfied for any choice of smooth functions. Now you can check easily that if the solution is smooth, then it is a weak solution, obviously, because you can integrate by parts. If the solution is a weak solution and it is smooth, then you get the equations. So it's compatible with the definition. I mean, those two things are compatible, but this is more general, of course, because here you don't require any differentiability of these functions here. As you see, all these functions appear only at the zero order, at zero order derivatives, which means that the only thing you need, not only that these functions should be continuous, it's enough if they are integrable. Everything what you need is integrability, in particular because we have seen that the density may not be even continuous, but still, even if you have a shock, it is still integrable, and so this makes sense. And so this is the weak formulation, and now this is a new framework. And so you may ask the same question. So okay, so now the first question is, if you give me the data, can I improve somehow my knowledge, and can I say that I have weak solution? That maybe the shocks represent a kind of continuation of my classical solution in the sense of weak solution. So well, what you can show is that what is called physically admissible shock, or well, not physically, shock which is somehow compatible with these two equations, is indeed, so it's a discontinuous solution of the problem, which is also a weak solution in this sense. On the other hand, however, it has been an open, it still is an open problem, whether or not for given initial data, without prescribing any other restriction, even for given smooth initial data, if you have a solution which would be weak solution defined globally in time. What is more, weak solutions are not in general unique. So let me say a few words about this. So the first problem is existence. Okay, so first you give me initial data, and they may be even smooth, but we have seen that even smooth initial data for some bad choice of initial data, or maybe for many choices of initial data, even the good solution at the beginning may become bad in the sense that there is a discontinuity in a finite time. And so you may ask, but can I prove that solutions can be extended in the sense that I have global solvability in the weak sense, in the sense of these integral identities? Well, the answer in general is we don't know. So you may find initial data for which you have global existence, but in general, the answer is still open. So basically, you can do something in the dimension 1. Again, I'm not going into detail, so I'm not saying anything about, say, the values of this gamma or the form of the pressure. But anyway, in the dimension 1, there are results which go basically back to Ronaldi Perna. And they are also based on the theory of the so-called compensated compactness by Luc Tartar, later on Gikian Chen, and also Lyons, Pertin, Souganidis. We are able to prove existence of global solutions, which for basically any initial data in the dimension 1. But the proof is really involved, and in particular it uses a kind of results like compensated compactness. It is not really trivial. Actually, this was published like 82, and I think here the final. And so the Pernas proof was sort of a little bit incomplete, I would say, and also with some restrictions on the value on the shape of the pressure function. Then Chen improved it, I mean, to a general gamma, but then finally the complete proof, I think, was presented here, and it was like 90 something, not really sure exactly, 96 maybe. So it took some time, right? Pierre-Louis Lyons, yes, not that one you like, or not that one we were discussing this morning, the son of Jacques-Louis Lyons, Pierre-Louis Lyons. So in the dimension 1, and the proof is technical, and the solutions are shown only in the class L infinity. They don't know anything else.
Sorry, you're looking for periodic solutions in space, right?
Yes, yeah, but that's not really essential here. In one space dimension, this is not really essential, if it's periodic or whatever. Okay, so now you may say, what happens when the dimension 2 and 3? This has been open for a very, very long time, actually. And people believe that, well, it's a difficult problem. So there are special results, for instance, the results for what is called a Riemann problem.
Which is still open.
I will tell you something about it. Just give me some time. So what is called a Riemann problem for this kind of equation? So for people who work in hyperbolic systems, Riemann problem is actually a problem with very elementary initial data. You take the initial data in which you already anticipate the presence of shocks. So for instance, you take the density which looks like that. But these are two constant states. So of course now you say it's not periodic. Huh? So I'm leaving now the framework of periodic solutions. I'm starting to work in solutions on the whole space. And then let's take the initial velocity, which is also of this type. And of course, because the initial velocity now is a vector, I have vector. I have each component of the velocity looks more or less like that. Then you can show that there is a solution of this problem. Actually, the solution of this problem can be written again as a kind of moving shock. It's a so-called autosimilar solution, and the solution is unique in a certain sense. Huh? It's unique in the class of autosimilar solutions, provided you assume something more. I'll tell you later. So there is, and there was a positive belief that the problem is difficult, and maybe if the data are more complicated, of course not all data are like that. The answer is in general not really easy to show. Now there was a breakthrough in a recent work by people like Camilo de Lelis and Laszlo Szekelydi. Actually, the work by de Lelis and Szekelydi was done for what is called incompressible Euler. But later on, a student of Camilo de Lelis, Elisabetta Chiodaroli, and also later on I also somehow work a little bit with Elisabetta and other people from Prague. So we were able to show the following thing. But I think that the essential thing is here. So they developed a strange method which is called the method of convex integration. And okay, of course I don't have time to explain how this works. But very roughly speaking, they construct solutions of nonlinear problems by means of constructing them by oscillations. So sometimes you know that oscillations are not good in nonlinear problems. For instance, you have an oscillating sequence. For instance, you take sinus and x. And you take n which goes to infinity. Now everybody knows that this sequence, not everybody, but in the basic course of function analysis, you know that this sequence goes to 0, but what is called weakly, right? This is a sequence which looks like that. If you take an average over any shorter interval, the sequence goes to 0, so this is the definition of the weak convergence. Now you would like, but this weak convergence, and but this is a very unpleasant property in the sense of nonlinear compositions. Because for instance, if you take sinus square and x, so this is like sinus n, the whole thing square. So this is a nonlinear function square applied to this weakly converging sequence. Now you would like, somehow these two operations to commute, meaning operations of taking weak limit and operation of taking the nonlinear function. But it's not true, actually. So what you would like is that this sequence converges weakly to 0, but it's not true. You can compute that the averages of this new sequence converge to some constant, depending on the sense. So the weak convergence doesn't have any. So if you want, if you take something which oscillates, but then you take a square of it, the oscillation sort of accumulate and create some extra value. And so that was actually, so people working in nonlinear problems don't like this phenomenon of oscillations, because this means if something like that happens in your solution sequence, assume that you have solutions which you construct by means of some approximation. If the solutions start to oscillate, then you cannot really pass to the limit on these nonlinear terms, because you are in trouble. And so it looks like that oscillations is a kind of enemy of people working in nonlinear problems. However, Delelis and Székely realized that it can be used also in a positive way, in the sense that this oscillating sequence somehow can approach somehow better certain nonlinearities. I mean, that's really very, very rough idea about the whole method. Of course, everything is much more sophisticated. However, they use this method in order to show very shocking results at the first glance. You take the same.
By oscillation, you mean oscillation in time?
Both. In general, some oscillations, yes. This is oscillation in space, actually. Actually, we don't know what kind of oscillation. Actually, the Euler system is known to admit these oscillations, and this is somehow, which means that you can find bounded sequences of solutions of the Euler system that oscillate. That's actually the growth of this method. And anyway, the result they obtained were sort of shocking. Take the same system of equation.
But for something that oscillates in space, this will not satisfy your secret axiom that the two far points are behave independently or almost independently, right?
Everything is local here, right? So you are talking about properties of solutions which are local. So this also, I don't think it has something. I mean, it's just about the behavior about some point. It has nothing. Maybe I was not very clear in my explanation. There is basically no time to really explain it well. I just wanted to say that there was a certain method. This is what I call breakthrough in the approach, or in the point of view how people see now the system of conservation laws like the Euler equation. Because by this method, by constructing solutions by sort of accumulating oscillations, they can show the following thing. Take anything actually for us. Okay, we can, let's take n. Actually, the point is that you have to take n is equal to 2 and 3. And let's take, so you exclude, this case is excluded, strangely enough. In this case, the method doesn't work because, roughly speaking, there is not enough space for oscillations. And so let's take these two cases which were considered to be difficult. Let's take any smooth initial data. The striking result obtained by the method of convex integration is that any smooth initial data, you have global in-time weak solution of Euler system. For any data. I mean bounded in an infinity and, sorry, not for any smooth. This is strange because we are talking about weak solutions, but you need the data to be smooth. I don't want to say how smooth, how you can, but at least continuous. So you get global in time solutions, which means on any time interval you prove that there exists a big solution of the problem. So this looks great, right? We can solve it, although the method is a little bit funny, but we can solve it. We know that the solution exists. Well, this is the good news. The bad news is for any data there are infinitely many of these solutions. For any data. Actually, infinitely many. So now you may already see some kind of little contradiction in my talk, right? I am saying that for any smooth initial data, we have global in-time weak solutions, but at the same time I am saying, and this actually holds for any, so this infinitely many holds for any time interval. So if you take even a very short time interval, even on this short time interval, you can find infinitely many weak solutions. So now I am cheating a little bit, right? Because at the beginning of my talk, I said, if I take smooth initial data, there exists a short time on which I have a classical solution, and this solution is unique. Well, the catch? The catch is that I said it is unique in the class of classical solutions. So in particular, these solutions I'm talking about here are really weak solutions. They are not classical from the very beginning. And so what is not so classical? So now, of course, such a result is shocking in the sense that you have infinitely many solutions. So actually, the weak formulation looks good for nothing, because if you have infinitely many solutions, you don't know what you are computing if you use your computers, because there are infinitely many possibilities. You cannot predict anything.
Most initial data you have infinitely many.
Yes, but weak solutions. This is the point. And so, and what these solutions do, what is so bad, what distinguishes them from the smooth solutions is the following thing: they are producing energy. And so this is the point. So now everybody started to think, well, so what kind of solution this is? We should find some extra condition which should be imposed on the solutions to save at least hypothetically some kind of physical relevance of this system. And so actually these solutions have the property they are producing the energy. What this means? Actually, if you go to the classical formulation and if you write down the energy for this problem, what is the energy? You multiply the momentum equation by u. You take the scalar product of the momentum equation by u. You integrate over omega, and you cancel everything what is like due to boundary conditions because of periodicity. And actually, what you find out is that if the solution is reasonable, you should have that the time derivative. Okay, so let me denote by omega this periodic box, because everything is periodic. So the time derivative of this quantity, where capital P of rho is actually related to the pressure. So I don't want to go into details, but if the pressure is this, then capital P of rho is A over gamma minus 1 rho gamma. So assume that gamma is greater than 1, for instance. And so you formally get that this quantity, so this is called energy in the problem, total energy, because this is called the momentum. This is kinetic energy, rho u square, and this is kind of internal energy, which means that you store some energy in the fluid if you squeeze it, right? It's because of compressibility. And so nice solutions should do this. If you start, this quantity should be not increasing with time, because formally you get this. Actually, you would like to have more. You would like to have some kind of equation for this energy, but roughly speaking, this is the basic requirement you need. And actually, these solutions don't satisfy this. For instance, they always, not always, but at least some of them apparently produce some energy, because this result holds also if you start with zero velocity and constant density, which should produce like constant solution. Nothing should happen, but still you have infinitely many of solutions. So this means that solutions constructed by the method of convex integration, they do, at least some of them, do the following thing. The initial energy could be like at the level 1, but immediately, after the initial time, the energy will immediately jump up. I mean, the most striking result is when the density is taken constant, which means that you start with zero velocity and you jump up with a velocity which is non-zero. And so you may now wonder in which sense you should understand, for instance, the initial value of the velocity in the weak sense, in the sense of oscillations. It is, the velocity is weakly continuous but not strongly, which allows for these jumps. So the solution, so you may say, okay, so now the physics and also mathematics is safe because, okay, they constructed very interesting kind of solutions, but still these solutions, they produce energy, so they are not physical. We should concentrate on solutions which do satisfy this energy inequality in some sense. For instance, you say this quantity, which can be easily evaluated even for the weak solution, should be non-increasing and should be always less than the same value at the initial datum. And this would, so, and there was a hope this would save the game. Well, finally, it is not the case, even if you insist on this. You can construct, you have the following result. So the result is a little bit weaker, but still striking. You give me the initial distribution of the density, which is smooth, so let's say it is in infinity and strictly positive. You give me, I am given this, any distribution of the density. The result is like that. Then there exists a velocity field, initial velocity field, which is not really regular. we will see. So it's only, what we know about this velocity field is that it is bounded and measurable. That's it. So it is not smooth in particular. And for this couple of, for this initial data, there is again infinitely many solutions that do conserve energy. There is no contradiction because now, for this, of course, apparently this velocity field cannot be smooth because actually we can show that solutions that do not produce energy, there is something what is called weak strong uniqueness principle, which means that if you have a weak solution which does not produce energy and you have a strong solution from the same data, they must be the same. But so apparently here this U0 is not a smooth data, it cannot be smooth datum, but for each rho 0 there exists U0 in L infinity only, for which you have again infinitely many of solutions. So it looks like, I have the last 2 minutes, so I should conclude. So now it looks like the conclusion is quite pessimistic, at least for the Euler system, because actually there exists initial data for which there is infinitely many solutions, even they are not producing any energy. So what else you can do? You can even, for people working in hyperbolic conservation laws, they tell you, okay, but you can impose some other condition, which means the other condition basically says that that the energy should also satisfy some kind of inequality. This inequality is called entropy inequality, and so you should work in the class of entropy solutions. But actually the same result can be proved also in the class of entropy solutions. So it looks like hopeless. Nothing can save the weak formulation and compressible Euler. However, there is maybe still some hope. There exists some hope, which of course there is no complete proof. That's only observation I could make also with Elisabetta and other people, is that the hope is the so-called principle of maximal dissipation. What this means? Okay, so actually this energy inequality, if you go to so strong solutions, smooth solutions should actually conserve energy because there is no dissipation, so you should have equality. For weak solutions, you expect inequality. Now, so let's define this function Et as the energy of the solution, which is a function, it's the total energy, it's the energy computed over the whole fluid. Actually, you can play with this. You can find some say local versions of this principle. So this maximal dissipation principle goes back to Constantin Dafermos. Very early, he proposed this. I think it was like 79. And the principle is like that. You say that the solution is good if there is no other solution which would somehow lose more energy. So weak solution lose energy. So you have a weak solution, the energy starts here. In general, the energy goes down. This is because on the shocks, actually, you sort of dissipate energy and create heat, but you don't see it in the Van formulation. So the weak solutions, they dissipate energy. So the energy looks like that. Now Dafermos says yes, but the right weak solution, so we have seen that actually the problem is not really very well posed even in the class of weak solutions. So according to Dafermos, he said, okay, so the right weak solution should be the solution which dissipates the energy at the maximal rate. There is some physics behind it. It's a kind of belief, it's a kind of a religion. Physicists believe that nature behaves in the way that the dissipation of energy occurs at the maximal rate. Which means that he says, okay, if you have a weak solution, and if you have another weak solution which coincides with your solution, but at a certain moment starts to dissipate more energy, like this is E prime, this is energy of another solution. If you have this solution is not good. If you find a solution which dissipates more energy, your solution was not good. So you can define an algebraic relation of, you can compare solutions, you can say that one is greater than another one if they are the same at a certain time, and then the other one dissipates more energy. And it's very rough because your energy is calculated over the whole omega, but you can also localize it and everything. And you say, okay, so the good solution is maximal in this sense, in the sense of this relation, which means if the solution is good, there is no other solution that would at a certain moment dissipate strictly more energy. And this, of course, this is extremely difficult to be checked. Such a principle, we know that this must be satisfied by by the strong solutions, because actually, as we know, strong solutions which dissipate energy are unique in the class of weak solutions. So the strong solutions of the problem are maximal. So there is no paradoxical situation that you can find some weak solution that would dissipate more energy. This looks promising. And the second observation is that if you go through the way how these solutions by convex integration are constructed, neither of them is maximal. For each of them, you can always construct a solution which dissipates more energy by the same method, actually. And so that's the conclusion of my talk. So maybe this problem is not completely lost. And maybe there is a chance to still save the Euler equations for mathematics and for numerical analysis because of this maximal dissipation principle, or maybe because of some other reason. So, so for people who really don't work in the field, I think the main point is these results. I mean, this is considered to be something really new. The results by Delelis and Szekelyidi, that's considered to be something like a groundbreaking result in fluid mechanics, because up to now, up to their result, people believe that basically some kind of entropy condition can always save this shock, the weak solutions for hyperbolic system. This is no longer true, but maybe there is still some hope. I think my time is up, so I thank you for your attention.
Thank you for this exciting talk. Are there any questions? Yeah.
Does this function phi and psi has any physical meaning?
Oh, these are called test functions. So you know these functions should be actually well, no, they are. This is for any. I was not very clear at this point. This should hold for any psi. The meaning of these functions is that they actually, well, these two formulations supply the original formulation, which was in terms of integral equations. So you take some space-time cylinder, you integrate your equations over the space-time cylinder, and you compare what happens on the boundary. But now, because so actually what you do is that you take characteristic function of this space-time cylinder, well, it could be smaller than this, and you integrate your equation and you compare the boundary terms. But of course, for solutions which are only integrable, there is nothing like a boundary value because they have no traces. And so the idea is to replace this 1 here by something which is almost 1, but something which is smooth. And if you do it like locally, then you get some kind of equivalence of this. So well, it's difficult to say they have physical meaning. I mean, it's just kind of, you can write this definition in many different ways. So some people prefer something else, but this is called the definition in the sense of distributions, all derivative. This is, but the physical background is actually like this. Normally, what you can find in textbook is let's multiply everything and integrate by paths, but actually it goes back to this picture here.
Any more questions?
So if you assume that you have maximal dissipation,
Yes.
the physical principle, okay, so I still don't know whether the solution is a weak solution is unique or not.
Okay, I don't know almost anything. What I know, if I assume I have maximal dissipation, I know that basically all solutions which are constructed, but it's not a theorem. You have to go to the construction, you present the construction, and you can see from the construction that for each solution which was constructed by the method of convex integration, you can construct by the same method another solution which dissipates more energy. So the method itself produces some counterexample. On the other hand, I cannot show that these solutions, I cannot show that solutions with maximal, let's call them maximal solution, I cannot show they exist, and I cannot show they are unique. This is still, I mean, if you could show, well, existence, I think it's very hard, because this would, I mean, you go back to the original situation before convex integration. But at least uniqueness would be nice. But uniqueness is difficult. Uniqueness can be shown in some classes of solutions. For instance, Dafermos could show uniqueness of these solutions in the class of piecewise smooth functions. So there were functions which are smooth except, I don't know, finite number of curves or even countable number of curves. However, we don't know that solutions obtained by these methods, I mean, not every weak solution is piecewise smooth. So we have uniqueness in the class in which you cannot exclude some pathological solution. So no, this is just an observation. That's nothing so deep in the last remark. Just maybe there is a chance.
Okay. And then there is another concept of weak solution in the sense of Krushkov.
No, Khrushchev fails. Khrushchev is not okay. No. Khrushchev is what is called entropy solution, which means that you get entropy inequality, which, this is a kind of this is actually entropy in my case. And so if you postulate some kind of integral, I told you, you can have something what is even finer than this. You can derive some kind of differential inequality for this. And this is what is called Khrushchev solution. And for Khrushchev solution, we can construct infinitely many solutions. But Khrushchev method fails. This is a system. This is the point. Khrushchev works well only for scalar equations. This is a system. We have rho and 3 components of the velocity. Khrushchev works only if the equation is scalar. So here, unfortunately, the Khrushchev. So as I say, actually these examples show that this approach by entropies is not enough. It's not strong enough in order to exclude some pathological solutions.